Yeah, and Arshad.
Okay. Hello, guys. Well, so thank you for joining us today. This is a little bit of a different session than we normally do, because we normally do kind of like paper reviews. But this was a really interesting blog post sort of that I came across, and I've been wanting to know a lot more about modern GPUs and some of the techniques that we can use to actually program them. So I decided to kind of make this presentation because I always find if I try and explain things to other people, then I understand it better myself as well. Uh, and now the blog post itself, it's quite long and it's actually got quite detailed, but a lot of it is about kind of the legacy GPUs. So I've kind of chosen my own kind of take on it. So this is kind of the outline of what I'm going to be doing. So I'm going to assume that you know a little bit about CUDA and a little bit about GPU programming, but then I'm going to kind of like really try and tell you about the new features in modern GPUs like Hopper and Blackwell and how they help us to do calculations like matrix multiplication. Matrix multiplication is actually really quite interesting because modern GPUs have got a lot of features to make it really fast. And if you know how to write kind of like state-of-the-art matrix multiplication kernels, then if you want to write other types of kind of kernels or other types of models, then all of that knowledge is actually really useful. So I'm going to try and give a little bit of introduction to GPU architecture, a bit about the CUDA programming model, but not that deep, and then all the key features that modern GPUs have, things like shared memory, barriers, tensor memory accelerator, and tensor cores, a little bit on the performance metrics, and then the actual matrix multiplication. So in Aleksa's blog post, he covers really three. One is a legacy kind of matrix multiplication. I'm not really going to be covering that because really that's nobody does things in that way, and it only really shows how hard it was to do in the past. And I'm not sure it's actually that interesting for the way we want to be looking at things. So I'm going to be really looking at modern GPUs. So that's warp tiling with the WGMMA, warp specialization, persistent kernels, and then I'm going to do a little bit about quantization because he doesn't really mention it, but that's actually a really super important topic. And then right at the end, some links to some resources that are actually worth, so if you want to kind of dig in a little bit deeper. Because so my whole aim for this talk is really to give you kind of like the lay of the land and some important mental models, and not go super deep into the CUDA C++, because I think that's probably kind of boring and it's hard to kind of like really get your head around it on just as a presentation. So that's how we're kind of going to do this. If you have any questions, just please feel free to raise your hands. So if we begin. So why study matrix multiplication? Well, matrix multiplication is actually really suited to modern GPUs. It's highly parallel. There's actually lots of different ways to do it, as we'll see. And it's kind of a marriage made in heaven. So as I say, so my aim is to kind of provide you kind of an idea of modern GPUs and some recipes of how you actually program modern GPUs. So if you ever actually look at a modern GPU, and this is like a card, the sort of card that you would fit into maybe your PC, then what you've got really essentially is this massive chip in the middle. This particular one, I think, is a H100 GPU. And then around it is the major part around it is actually the global memory, which is called HBM, which is the high bandwidth memory. This is usually quite large. It varies, depending on the card that you have, it could be 40 gigabytes, 80 gigabytes, up to 190 gigabytes. So it depends on the particular card that you've got, how much memory you have, but that's in the gigabytes. So there's quite a lot of that available. So this is actually on the GPU card. So this is not your CPU. Your CPU itself may have lots more memory because that's cheaper. HBM is actually very expensive. So even though it's reasonably large, it's not as large as we would like. Okay. So if we have a look kind of like just conceptually, what is kind of like the architecture of a GPU? Then on the left on this diagram is basically, this is your CPU over here. So you've got CPU cores, the memory in your computer, and then there's some kind of a connection to the GPU, which is either over PCI Express or NVLink. And the GPU then is kind of like broken up into what are these called on the right-hand side, which are these streaming multiprocessors. Now, you don't have like hundreds of these, so it may range between 120, 130, depending on the kind of GPU you have, up to maybe 190, but there's certainly not thousands or hundreds of thousands of these. And these are kind of like the CPU on the GPU. So each of those kind of work independently. And then you've got some cache on the actual card. So that's kind of like the top level view of that. Now, as I say, the SMs, the streaming multiprocessors, is really where all the action takes place. And as I say, there's not hundreds of those. There's usually maybe just 120, 130. But each one of those has got quite a lot of kind of circuitry. And the main bits there are things like the tensor core, and that helps to do matrix multiplications in hardware. And then next to that, there's other compute, and these are things like your sine functions, your cosine functions, log function. So they've got functional units for that. Then you've got a warp scheduler, and we'll come into a warp side in a minute, but that's basically a bit like the CPU kind of scheduling programs, and you can think of warps as programs. Then you've got some memory circuitry for load and store into memory. And finally, you've got a register file. And GPUs are quite nice because they've actually got a lot of registers. So each one of these SMs, and there's say 130 of them, actually has 65,000 registers. And these are the fastest kind of like way to do calculations. So unfortunately, they're not unlimited, but there's quite a few. So there are 65,000 of those. And then each of these SMs has also got an area called the shared memory. And this is actually super critical, because this is really what you need to use to get like the highest performance in kind of like modern computations. And we'll come to that in a minute as to how that's used in all the matrix multiplications. And so as I said, each one of these is kind of like specialized, and you've got about 130 of those. Typically, they can go up to 190, but your typical is about 130 to 140 of these guys. So if we carry on, and then each one of those SMs is further broken down into 4 basically units. And each of those units has got a tensor core, and it's got all these floating point operation type units, and then it's got load store into memory. So essentially, you can think of it as each of those SMs is capable of running 4 programs simultaneously. And we call those programs warps. And each one of those warps has 32 threads that are actually operating. And we'll come into a minute into how that kind of breaks down. But so essentially, at any moment in time, you can have 32 threads running on the top left one, 32 threads on that one, 32 threads on this one. So 4 times 32. So at any point, there's could be 128 threads running on a streaming multiprocessor. And you've got 130 or so of those. So there's quite a lot of threads actually running. And as you can see, kind of GPUs have kind of a lot of complexity in the hardware. And to be able to really write high performance kernels and high performance code on a GPU, you kind of got to know its hardware, because you can program at the level of this hardware in your kernels. Knowing this information and how it actually kind of works is super useful. And really, this is kind of the secret of getting really high performance from your GPU code. So if you look at any particular one of those, one of the most critical bits, is this thing called the tensor core. And essentially, this was added a couple of generations back, but in Hopper and the very latest GPUs, basically, so tensor cores basically do matrix multiplications, but in actual hardware. So a single instruction can do, say, a 16 by 16 by 128. So when we put these 3 numbers, what that means is that the matrix, so your left-hand matrix is 16 by 16, and your right-hand matrix is 16 by 128. So the overall compute, so that's what these 3 numbers mean. In Hopper, I believe you can do 128 by 64 by 16. So you can so that's the size. And in Blackwell, you can actually do 256 by 256 by 16. So they're not massive matrices, but essentially you break your original matrix down into these kind of tiles. And because each one of these can be done in hardware in a single instruction, this is one of the fastest ways to actually do the computation of your whole matrix multiplication, basically. So these tensor cores are going to be critical to getting the best performance on a matrix multiplication. Now, one of the most critical things that we need to kind of like understand when you're working with GPUs is this notion of a memory hierarchy. Unfortunately, as with all with life, so in here, we're looking at all the memory that's actually available on a GPU. So right down at the bottom are the chips on the actual card. This is called device memory or global memory or HBM. This is reasonably large. It's between 80 gigabytes, typically 90 gigabytes, can go up to 190, but so it's reasonably large, but unfortunately it's extremely slow. Slow in the scheme of things because it's still 3 terabytes per second getting data from global memory onto the chip. But as we'll see, as we go kind of up the hierarchy, where so things speed up basically. So the next level is actually L2 cache, and this is actually on the chip itself. So the device memory is on kind of separate chips that are on the card, but from L2 up, these are things that's actually on the chip. The L2 cache, which is the SRAM, which is shared memory, is 12 to 14 terabytes per second, so about 4x the performance. Distributed shared memory is basically multiple streaming processes able to share their SRAM. We're not going to be really super covering that, but potentially that's available for next generation kernels. So if you're writing a kernel where more than one streaming multiprocessor is cooperating on the task, then you can use this distributed shared memory to actually be able to communicate amongst those streaming processes. The next level up is L1 cache, which is again closer to the actual streaming multiprocessor. And again, you're getting around 31 terabytes per second. And right at the top is register memory, which is you're getting maybe 124 terabytes per second. So really, the secret to a high-performance kernel is the top kind of 3 layers here. But the shared memory. So the very bottom one, which is the device memory, ideally you really want to avoid going to that if at all possible. And even if you do, you've got to kind of try and batch off your operations to it so that it can be as efficient as possible. Because any time when you're going back and forth to global memory, it will be an absolute performance killer. And usually the performance difference can be 10x between a kernel that really makes effective use of shared memory and the registers compared to going back to global memory. So this is a critical thing. You'd have to kind of see what your kernel and see what the memory access pattern is, and this will be kind of like a critical component of that. Now, going to like the CUDA programming model. So essentially what we tend to do, what we do is we write a piece of code which we call the kernel. And we think of that as kind of working as like a particular thread. So that kernel is really only aware of itself. Typically, it's not aware of other threads, although it can kind of like synchronize with them. And then when we launch like a kernel, which is when we launch software on the GPU, then that is it's kind of like broken down into grids, blocks, and threads. So basically, grids are kind of like a logical concept, and so if you imagine what a grid defines is how many blocks are going to be executed, and then what a block defines is how many threads are going to be executed. So when we launch a kernel, we say we're going to so in the second bullet point where you got in the second bullet point, which is the kernel launch parameters, we kind of say to it, okay, we want this number of blocks, and then within each of those blocks, we want this number of threads. So those are typically the parameters. more modern GPUs like Blackwell, actually a Hopper as well, add a level called cluster. So you can actually kind of force some blocks to be next to each other on the GPU, but we're not going to really cover that. There's not a huge number of kernels that may take advantage of that yet, although it will be more important later on. And then we just mentioned the memory hierarchy that we've got. So as I said, we want to kind of stick to near the top. So I don't know if anybody has any questions about that. I know I've kind of gone through this pretty quickly. Okay, so carrying on. I have put sort of references at the end of in resources if you wanted to kind of like, there's a couple of blog posts which will take it a little bit slower than sort of the pace I'm going, which will kind of explain in a little bit more detail. So you can get back to those. So, so going now into the features of modern GPUs. So the first of these is shared memory, which is actually super critical. So ideally, you want to do as much as possible, either in shared memory or in registers. And the benefits are obviously is the incredible high bandwidth that we get from shared memory into the compute units like the tensor core, or the compute, the functional units like sine, cosine, and log. Incredibly low latency, 10x difference compared to to global memory, to shared memory. And modern shared memory also supports asynchronous. So this is another feature of modern GPUs, is that you've got to get comfortable with doing asynchronous computations, because ideally you don't really want to be waiting around for data to arrive. You would rather issue an asynchronous memory operation and then find something else to do in the meantime, because that's going to make the most effective use of your GPU. Any kind of waiting around is obviously just wasting resources. So that's kind of shared memory, super critical to get a handle on what you've got and how to use it. Now, there are some gotchas with shared memory. It would be nice if we said that there is 256 kilobytes of shared memory and it's just available for you to use. The issue is that actually most memory, and not just shared memory, is always actually broken down into what are called banks. The way banks work is that, so in this case, the shared memory is broken down into 32 banks. And the way it works is that if you read any thread issuing a call to read some data from a bank or write some data to a bank is serialized. So if two threads try and write to the same bank or read from the same bank, then one has to finish before the second one can start. So if you have bank conflicts, this is going to massively slow down your kernel, because essentially every access to that bank between the threads is going to be synchronized. The way to avoid it is to actually kind of spread your data across the banks. So one thread reads from one bank, another thread reads from a second bank, a third thread reads from a third bank. And then all three of those can be done in parallel. So that's really the pattern that you want to adopt. If you see any kind of bank conflicts there, that will be a killer. Modern profiling tools will kind of give you statistics on whether you're getting bank conflicts in your kernel, and then you can use that to kind of debug as to what memory access that's actually causing that. The other problem with shared memory is that it's fantastic, but it's very limited capacity. There's only 228 kilobytes of it per streaming multiprocessor. So instead of the gigabytes we had in global memory, this is very small. And then the other issue we have is that synchronization is required. Basically, because we're running, when we run code on a GPU, we're using many threads. And the CUDA programming model only really guarantees that if you made reads or write, so if one thread has written something and the other thread wants to read that data, that until you've synchronized across all the threads, that second thread is not guaranteed to be able to read that data. So you need additional synchronization if you're kind of doing the kind of computations where one thread is writing something and then another thread needs to access that. And syncing threads, again, it's one of those places where the kernel will have to wait until all the threads have reached that point, and then you can carry on. So Sync thread is sadly needed, but it will be potentially a bottleneck. And if you can avoid it, obviously that would be the best. And the final is occupancy trade-off. So basically, every thread needs a certain amount of, every block needs a certain amount of shared memory. And the problem is that the streaming multiprocessor has only got 228 kilobytes of it. So if you've got somehow a kernel which is where the blocks are needing to use quite a bit of memory, it means that the number of computations that can be done on that streaming processor is limited, and this is called the occupancy level. It's basically the number of blocks that can actually fit on a streaming multiprocessor. Again, profiling tools will tell you what your occupancy is, and the issue is going to be that if your occupancy is low, then basically not as much stuff can get done on that streaming processor because one of your blocks is using too much memory, and it just means that other blocks can't get started because there's just not enough memory to go around. So ideally, you want your occupancy to be as high as possible, so as much stuff can run in parallel on a streaming multiprocessor as you possibly can. So these are kind of like the things you have to look out for. Profiling tools can help you by giving you statistics on this kind of stuff as to whether you're having these problems, so you can debug them. The next thing is, so we just mentioned this thing to do with bank conflicts. This is the thing where two threads cannot access the same bank. And the way to get around this is this topic called swizzling. And in the past, this was actually really complicated to do. But modern GPUs have made it like super easy, but because you can just define like a constant in one of the descriptors. And basically what's happening here is that if you, on the left-hand side, we've got some memory and global memory, and we're copying into shared memory on the right. And what's happening here is that the data on the left is actually being swizzled on the way onto the right. So the data on the left, you can see, is nicely ordered. But the data on the right, it means that if it's possible for you to, for instance, on the left-hand side, if you were reading the left-hand column, which is 001020, if it was like that in shared memory, and you had multiple threads, and they each wanted to read one element of that would mean that they would all have to be sequentially read, because that's the same bank. So these colors are basically banks. But on the right, because of the swizzling, your data's like, if you can see that column is actually now on the diagonal on the right side. So if it means that if one of our kernels need to read that whole column, then it can be done in one cycle, because each one of those is now on a separate bank. And this is done automatically for us. So when you copy data from global memory to shared memory, the instruction, which I'll tell you later, which is the tensor memory accelerator, you just tell it to do this and it'll do it for you. But in the past, we had to manually do this, and this is why historically all these kind of calculations were really horrendous. And this is why Aleksa goes into quite a lot of detail about what swizzling is and how that computation is done. But because this is all done for you now, it's good to understand it, that if you are having bank conflicts, that you're maybe messing this up, or you haven't quite enabled it properly. So this is something to be aware of. So swizzling is super important. The performance difference is quite literally 10x, because on the left, everything is going to be sequentially done, whereas on the right, everything can be done in parallel. And this is a massive improvement in performance. So going on to another feature, barriers. I'll say most modern matrix multiplication kernels are going to be relying quite a lot on asynchronous operations. And what that means is that obviously some thread is going to make maybe some memory read asynchronously. Some other threads will need to wait for that to arrive. And the way to coordinate that is what are called barriers. And barriers are basically a way of a certain thread to say, I have carried out this operation and the data is ready. Another thread to indicate, I am waiting for this operation to have completed, or a whole bunch of threads. And barriers are the way to do that. Barriers are super useful. The only gotchas are that a lot of the patterns are quite complicated. So they're easy to mess up, unfortunately, and you get sort of like deadlocks or even invalid kind of code because you try to do things in completely the wrong way. So they are super useful, and they enable a whole load of like really powerful patterns in modern GPU code, but they are, as the gotchas would say, they are kind of complicated, and even the code is kind of complicated to read as to exactly how everything is being synchronized. They're easy to deadlock if you've messed up the way the barriers are being used. And they have got limitations as to how many threads can actually cooperate in terms of synchronization. And in the old days, you just used to do sync threads, and all the threads would synchronize. So these things are very powerful, but as I say, they are pretty difficult to debug if you've messed it up, unfortunately, which is super easy to do if you're not 100% like clear on exactly how they work and what your requirements are. So carrying on, another super important feature of modern GPUs introduced in Hopper is the tensor memory accelerator. So basically, a lot of times we need to copy data from global memory, which is into shared memory to do the calculations. In the old days, you had to do this manually. Each thread would have to sort of copy some bit of data from global memory onto shared memory. Well, this has been super simplified now, and it's been made into a single instruction, async instruction. And essentially, you set up a descriptor which kind of tells the tells the hardware unit, which is going to do the copying, what the shape of your data in global memory is, where you want the data to be copied, what swizzling operation you want to apply, which we just talked about a minute. So this is the bit that will do that for you. And in the old days, you had to have to do all these kind of like really weird memory calculations to be able to, particularly if your tensors are a bit more complicated. I mean, this supports up to 5D tensors. So all the manual address calculations, which took time, and registers are no longer needed because everything's done in hardware. So this is like a super important thing to get your head around if you're building any kind of modern the high performance kernel. This is one of those really critical elements. The only gotchas are the descriptor is actually non-trivial because you're setting up so much data, telling it about the shapes of your tensors, where you're copying it to, the swizzle pattern, and there's quite a few other sort of parameters. To actually use it properly, you do need to know exactly what you're doing and exactly where your data layout is in your global memory. It does need you to use barriers because this is an asynchronous instruction. So again, adding that, it makes it a bit more complicated. And really, it works best if your data is properly laid out in global memory. And by that it means you're accessing it in kind of like the layout is just is strided in just the way that this works. Again, because it's asynchronous, it makes debugging difficult. If you messed up the layout somehow in the way the tensor is laid out in global memory, that can make it tricky because at least in the old days, you were doing the calculations, but this is all being done for you now. So debugging is a bit more complex. Debugging in modern kernels is always complex now because there's more kind of like async stuff going on. So that's the tensor memory accelerator. And finally, the tensor core. So basically, this is a hardware unit to do matrix multiplications, quite large matrix multiplications. It's asynchronous. There's some assumptions it makes about where the data is. So as to whether it's in shared memory or it's in registers. And this is really one of the most critical kind of like technologies to make matrix multiplications super fast on modern GPUs. So again, this is a really critical component to understand. And it is a little bit tricky because multiple threads actually cooperate to do this calculation for you, or even though it's in hardware, there's some certain requirements as to exactly how all the threads need to actually execute this instruction to actually get the full performance. that you actually want. Now, there's quite a lot of like niggly bits in here about sort of alignment and kind of like the memory layout and shared memory. There's only a limited data type support, so not every single data type you're interested in would support this. All the popular ones do, like BF16 and FP16 and Intake, but some of them are either just emulated or they just are not supported at all. So you do have to kind of see if the particular data that you're interested in doing is even supported by these guys. It's probably one of the most complex instructions you'll see in CUDA because it requires so many parameters. There are libraries like Cutlass and QDSL that really help with this. So if you don't want to write raw CUDA code and you just want to use like a library, that's that might be the way to go. And you still get probably 90% of the performance of CUDA with those libraries. Rather, obviously not 100%. Because you would really need CUDA for that. And there's issues to do with occupancy. And I'd say this is probably one of the most complicated kind of like bits of modern code, but it's really the supercritical one because this is really where the power of the matrix multiplication kind of like becoming efficient on modern GPUs is. So again, if you're interested in, then this is sort of like the tensor core architecture, and the WGMMA is really where you need to get your head around. In terms of performance metrics, typically we measure them in like really, the main one is arithmetic intensity. So what we're really interested in is, are all the compute units basically busy, and how busy are they? And typically this is measured by the number of floating point operations that your kernel does divided by the number of bytes that are transferred from global memory. Because essentially, because global memory is so slow, the denominator in here being larger will really kill your performance. So higher arithmetic intensity means that your kernel is basically more efficient. Now, so that's arithmetic intensity. The second is speed of light. Typically, you may find it hard to calculate, but sometimes I've seen people say, okay, this particular card is capable of doing this is the speed of light. So, for instance, if we wanted to do matrix multiplication, then the easiest or the simplest kind of like algorithm is order. If it's m by n, then it's m times n, order m times n. And if we know that that's the number of floating point operations we're going to need to do, then we can say, okay, what is the maximum possible speed on a particular GPU? Because we know it's kind of like how many floating point operations per clock that is capable of. So essentially, speed of light is the maximum possible throughput for a device. And you can then see, okay, I need to do m times n calculations. How close am I to the maximum speed of light? And for some people, I managed to get within 10% of speed of light. So you're really using as much power as the GPU is possibly capable of with those. The other issue to be aware of is thermal throttling. It depends on whether you're doing something which is like super critical and you really, really care about how fast it is. Unfortunately, modern GPUs, to kind of protect themselves, they do kind of, depending on the heat on the chip, because they have a sensor for that, they will reduce the clock speed of the GPU to kind of stop overheating. So if your GPU is being thermally throttled, then that can just mean that your code runs a lot slower. So it's not your fault, it's just the thermal throttling there. And for the guys who are really into this, they really care about this kind of stuff because even the temperature in the data center matters for this kind of stuff. So it's something worth kind of knowing if you're really getting your speed of your kernel is really slow, you just can't explain it. It might be worth looking at what clock the GPU was waking up at because it might have been thermally throttled. Okay, next. So the other thing you might come across is what's called a roofline model. And essentially, it's kind of like a plot for a particular GPU of, it's kind of like peak performance per memory load. So the two axes here are the arithmetic intensity on the x-axis and the performance in flops per second on the y-axis. Essentially, if you know your algorithm is at a certain arithmetic intensity, and you're getting a certain performance, then it can tell you whereabouts you are and how much kind of leeway you have to push your performance higher. And essentially, you would do that by optimizing your global memory access, because that is going to be probably the biggest win for you. So let's say sometimes you come across these kind of plots, so it's worth knowing what it represents. But it's only kind of like giving you a qualitative kind of feel for where your GPU kernel is. It doesn't really give you massive insight into exactly what you need to do, but it's worth comparing it sometimes as to to see where are you and how bad you're doing compared to what the theoretical possible is. So finally getting to matrix multiplication. So obviously Aleksa's main topic in his blog is the matrix multiplication. And this is kind of the most trivial way that you might do a matrix multiplication. So if this is kind of 4C. So essentially the top one, for instance, the first loop is going through, say, the rows. The second loop is going through the columns. And then we're doing a dot product of those two in the final for loop in the middle, and then setting the result in the output tensor there at matrix there, C. So this is the way you might write it on a CPU. It's not super optimized. And one of the biggest problems in here is the one right in the middle where we said temp plus equals AFM/K. Well, that's reading global memory times B for K/N, which is also reading global memory. So this is individual cells being read from global memory. Well, that's going to be a killer, because anytime you read from global memory, it's going to be super, super slow. And if you're reading one element at a time, then that's going to be one of the slowest possible ways of doing things on a GPU. As I said, I mean, obviously, you might be lucky, and the compiler could do some loop unrolling and might notice some of these things and do some vectorization for you. But if you just look at it the way it is, it's going to be horrendous. But one of the things that's worth noticing is that actually the three loops are not actually related to each other. So there's no reason why we have to do M on the outside, N within it, and then K within that. We can actually swap these three loops around. And because there's three loops, there's actually 6 variations. But as Aleksa mentioned, one of the most interesting ones is if you take K right on the outside. So this is doing that same calculation, but doing it in a slightly different way. So it's going through the common axis K, and then within it is doing, say, the rows M, and then reading that particular value of K, and then accumulating that in the inner one, which is the column. And why is this one interesting? Well, this one's reading a lot less from global memory, because in the last one we were reading right in the middle where we're accumulating the result. We were reading 2 reads from global memory. Well, now we've stopped doing one of those because we moved it outside of the inner loop. And this is a massive saving to do that. And there's no reason why that has to be an individual cell. We could make it like a tile of data. So instead of K going, one step at a time, we could go, we could say, okay, well, K is going to be broken down into N tiles. And that would make it even more efficient. So this particular variation is what a lot of modern kernels are kind of written as. And he kind of puts this in this diagram now. So his first kind of matrix multiplication algorithm is to do it this way. So you take a particular tile of the A matrix, a particular tile of the B matrix, you do the calculation, and then you accumulate the result. And essentially, you kind of sweep down the row from one matrix, sweep across the columns on the other matrix, do it tile by tile, and then finally compute the result. And this is actually quite an efficient way of doing it, and that's kind of like the first the first kernel. And so why is it efficient? Well, first of all, because we've broken into tiles, we can bring all of that data into shared memory. So even though we are reading it from global memory, we move the data into shared memory before we do the computation. And the reason we broke it down to tiles is because unfortunately we can't bring the whole row in one go into shared memory because there's probably just not enough. But if we have if we break it down into individual tiles, then we have got enough shared memory. And because all the computations are being done in shared memory, this is one of the fastest ways to actually do those computations. So essentially, so the key insights in this first one are, instead of computing individual cells of the app matrix, we compute a whole tile. And we copy the tiles into shared memory and then do the computation. And why do we do the tiling? And actually, most modern kernels, they will make use of tiling in some way, because essentially it's a way of making the most effective use of shared memory. Because it's not infinite, we can't do the whole of something. But if we break it down, the problem into tiles, and if you make the tile sizes sufficiently fit in shared memory, then that's going to be a really excellent way of doing this. And this was the state of the art on architectures without asynchronous operations. So this was the first algorithm he covered. So this is basically it. You break it down to tiles, copy the data to shared memory, do the calculations in shared memory, accumulate the result, and then finally write out the result to global memory. Okay. So what's the problem with the tiling? Well, so so the way we did it was we break it down to tiles, we load that data into shared memory, then we carry out the compute, and then we finally store the data. Now, the problem is that while we're loading, while we're storing, the compute units are sitting there idle. They're not doing anything. And it would be really nice if we could somehow interleave the compute and the memory loading, because then we could keep the compute units busy all the time. So somehow we would have to kind of say, okay, we're going to load memory for the next tile while we're computing this tile. And that would be a way of kind of interleaving it. And that's basically this idea of the producer-consumer. And this is one of the kind of like a more modern matrix multiplication. So essentially what we're doing here is we're kind of like breaking apart the calculation into different warps. So one set of threads just loads the data for the other set of threads to actually work on it. And although in this case we're only using kind of like and this is, you can actually have a buffer of data that the first thread loads. So you don't only have to have one. You choose the buffer size to make your other units as busy as possible. So essentially what we've done is we've said, okay, one of these guys is totally responsible for loading data from memory, because that's really slow. So we will try and load everything as much as we can, and where the other units will be responsible for doing the calculations. And we basically choose the sizes of the buffers and the tiles to make this as effective. And one of the nice things here is that your tensor unit will now be occupied all the time if you've done this properly. So you're going to get the very best performance out of your GPU by doing this kind of interleaving. So this is called warp specialization, because you have one warp dedicated to actually loading data from global memory into shared memory, and then other warps which are responsible for actually doing the calculations, and they're always busy because you've always got data ready for them, because that's being done in parallel to when the calculations are being performed. So that's the second. Again, you can get like quite a significant speed up from doing that. Okay, so what's the okay, so that was actually quite nice. The tensor units were busy all the time. We got a lot of computation done. What's wrong with warp specialization that we want to look for some other alternative? Now, the problem is depending on your problem, it might be that it fits really nicely on your GPU. You might have been able to break it down into so that everything is kept busy. But the problem is that this doesn't always happen. So you might have a problem which just cannot be broken down in like a nice way. There's some bits of it that just still are left over, and then you've got the GPU not really super busy, but making, taking a whole lot of extra time just to finish out this extra calculation. So, and there's scheduling overhead as well, because you might be, depending on how you've written the kernel, you might have written it as more than one kernel, although, that's another use case we have. So that's kind of like the algorithm 3. And this is kind of like pretty close to, well, I guess what state of the art is now. These are called persistent kernels. And the way you do this is you say, okay, I've got a certain problem, and I've got a certain GPU with a certain number of streaming processes. What I really want is all my streaming processes to be as busy as they possibly can be until all my work is done. And I want them to kind of like, so what I would really like to do is to create kind of like a work queue. And then the streaming processes, they'll be running all the time, and they'll just pick stuff off the work queue and actually get it done. And that would mean that really, the worst case is that one of these streaming processes got a tiny little bit to do, but everybody else is always super busy. Obviously, again, you have to kind of like partition the work, or it depends on how you create the work queue for the kernel. But if you do this well, and there's a couple of algorithms that people have created, one's called StreamK, and it just pushes your performance just a little bit further by getting rid of that overhead, and by making it a bit more flexible. That if you can't quite partition the work properly with the previous kind of approach. So these are kind of like the more state of the art kernels are using persistent kernels. So this is one other approach to be aware of. Finally, Aleksa didn't really mention quantization, which is unfortunate, because actually this is super important. Traditionally we were used to doing everything in FP32, but actually, depending on your problem, it might be that you don't need the full amount of your, of the precision on your data, and you may be able to get out with a lower precision. And essentially, each time you halve the precision, you're doubling the performance. So if you're going from 32-bit to 16-bit, doubles. Going to 8-bit, again doubles. And then if you're going down to 4-bit, again doubled. And actually, these lower bits have got scale factors, and the NVFP4 is particularly quite an interesting one because of the way it does it. You can actually get pretty good performance, up to 80% of the precision of your full FP32 from these low precision. And obviously, the performance is massively improved because at NVFP4, you potentially get 8x the performance of your FP32. So these are like super important to know. And it may even be in future, a lot of LLMs are trained at FP8, because people have tried that, and that seems to work really well. I don't think people have really tried NVFP4 that much, although that was really only released in the Blackwell, sort of like last year. But quantization is going to be super important, and if you can use a lower precision, then you just get an easy win on your particular problem. So that's quantization. And finally, he gave some statistics. So I'll probably just go through this. So basically, he's gone a couple of different approaches and how the performance has improved. So the particular GPU he was working on, I think, is capable of 1 petaflop, which is 1,000 teraflops. So the very first, so basically the very kind of traditional way of doing matrix multiplication, which is the top one here, he was getting 32 teraflops. That's basically 3% of the GPU, basically. But once he did algorithm 1, which was tensor cores and tensor memory accelerator, so that performance jumped 10x. And obviously the swizzling and getting all the memory accesses aligned, that went to 317 teraflops, sort of pretty much straight away. And that was not a super complicated kernel. And then increasing the tile output size, because he had a particular size. If you could kind of like slightly look at how much shared memory he had, and he increased the tile size, he was able to push that to 423 teraflops. which is almost 50% of the GPU now. And then he did a pipeline, which I didn't cover, which is a particular approach where you, because of the async within a particular warp, you can do this called pipeline. That pushed it up a little bit higher, up to 498. Again, and a bit more tile growth to 610, and then persistent kernels, which took it up to 660. Then he did a couple of these. So faster PTX barriers is a particular low-level instruction he used. That pushed it up a little bit more. Clusters, which I didn't cover in here, which is essentially multiple streaming processes being next to each other and being able to kind of cooperate. That pushed it up a little bit more. Some more micro optimizations, 747. Tensor memory async operations up to 758. And finally, he did some Hilbert curve thing, which only pushed it up a tiny bit to 764. I haven't covered Hilbert curve because I hadn't really seen it used in the wild that much. But you're almost 80% of the GPU performance there, really. So, it's pretty good going from 3% up to that. And as I said, the main important ones there are really the persistent kernels, and the original one, which was the Tensor Core TMA, and both of those are, at least the TMA one is reasonably easy to implement. So that's definitely worth trying. So conclusion: modern GPU programming, you've got to get like a really solid mental model of the hardware and the instructions you have available and the size of your shared memory to make effective use of it. You've got to get comfortable with asynchronous programming and being able to debug asynchronous code. Your profiling tools will tell you about your memory access patterns, whether they're coalesced or not, and whether the cache is being effectively used. That's another usual pretty easy win. And the difference is 10x really between memory access that are coalesced or not. And things are now warp level. So basically, traditionally, you worked at a thread level. Now you kind of think about, okay, I've got this set of 32 threads and these other 32, or even a warp group with 128 threads. Okay, how are they cooperating? And cooperation among threads is going to become more and more important because NVIDIA introduced a thing called a cooperative group. And that allows a lot more flexibility as to how threads can cooperate amongst each other compared to traditionally. I haven't covered that, but that's, again, going to be like super important. Finding some resources there. I'll provide these slides. As I said, some of those blog posts, things like outperforming cuBLAS on H100, which is number 3, that's a really good one. And the modular, which is number 6 there, which is matrix multiplication Blackwell, that's a really good set as well. It covers the hardware, and there's actually 6-7 kind of like parts to it, but it's super useful as well if you're really interested in kind of modern GPUs. And kind of, yeah, I mean, that's the presentation. I don't know if anybody's got any questions.
Thank you, Arshad. That's amazing. Yeah, we have a few questions on the chat. Let me scroll from the first question. The first question was about, repeating. Can you please repeat the relationship among grids and blocks? Yeah, if anyone wants to clarify the question, just
okay. So when we launch a kernel, so if I go back to the, this can be quite confusing because we call it like a grid. So let's put the CUDA. Oops, with the programming one. Okay, so when we launch a kernel, we give it usually 2 parameters. One is the grid dimension, and then the other is the block dimension, which is really confusing because it really, what the grid dimension is telling you is how many blocks you want to execute on the GPU. So, and each of those is actually 3-dimensional, although, unless you've got, your problem is easy to logically break into that, we normally use just the 1 dimension each. So, okay, so let's say you did grid dimension of 10 and block dimension of 10. What that means is you're going to start, because grid dimension is 10, you're going to start 10 blocks, And because your block dimension is 10, it means each one of those blocks will have 10 threads. So that's the way it works. So finally, on your GPU, you'll have 100 threads because you started 10 blocks. That was the grid dimension, and you started 10 threads because that's the block dimension. As it is confusing, because in some sense it makes more logical sense to be able to call the first parameter block dimension to say how many blocks you're going to execute, and the second parameter should be thread dimension to say how many threads per block you would have. I know it's kind of confusing, but yeah. So the first one is really how many blocks you're going to execute, and the second one is how many threads within each block you're going to execute.
Cool, thank you. We have 1 minute left, but there are 2 questions, so we can discuss it. First one, are there any considerations related to GPU CUDA programming and resource management when it comes to the neural network type used to train and infer on it the GPU, like CNNs versus transformers?
Yeah, so modern GPUs, yeah, I mean, there are things like how much shared memory that you're going to allocate to the kernel, the maximum number of registers that it should have available to it. So there's quite a few parameters. Because the different GPUs in the series have got different, you would have to look at the CUDA documentation on NVIDIA's. But yes, there are mainly to do with what resources on the chip, things like the number of amount of shared memory and the number of registers. Those are the 2 main ones.
Thank you. Okay, last question.
I was the one who had the other question.
yeah.
Sorry, I had a different question. My big question here that I don't know if there's an easy answer to is ragged data. So this is fine for like full size arrays, but like, is that just a hard problem, or is there any solution to ragged data other than just padding it out to a full size array and then running that? Is there any kind of solution that's coming for that?
I mean, really, as I say, when you say ragged data, are you talking about sparse data, or are you kind of like, or is your
sparsity would be
problem just?
Yeah, sparsity would be one way, but I mean, like, I'm talking about GNNs that have like variable size. Sorry.
Yeah, I mean, the issue is going to be that really to get the best performance out of a GPU, things need to be aligned and things need to be coalesced. And this is why, I mean, you'd have to look at your particular problem, but typically padding may not be the worst thing to do because, your memory accesses would be coalesced. I mean, I would kind of try and pad it unless that was going to add such a huge amount of overhead to it. It would also kind of like, it might be that you don't need the worst amount of padding because it depends on, because I say a lot of access in modern memories, they like things to be aligned to certain boundaries, like 16 bytes. And then they like things to be coalesced, which is like you're going to read things which are like sequentially. It depends on whether you're in global memory or shared memory because they've got this bank complexity. But as I say, and it depends on how you partition your problem as well, because sometimes padding it might make the partitioning a little bit easier. As I say, as soon as you say something like ragged, I would say, okay, well, that doesn't sound like a great idea because the stuff will not be aligned and you won't get coalescing. So I might be tempted to kind of pad it, but I'd have to look at the particular problem and exactly what the kernel's doing. But intuitively, I think it sounds like you might have to pad it.
Yeah, fair. Thank you.
Yeah, one really last questions because we are running over, but this has been really good. Okay, last question. Is this all applicable to edge devices, or what will be the key difference to be aware of?
So depends on your edge. I mean, it depends on your particular use case because I mean, it's slightly speculative. Right now, a lot of the edge are like CPUs. Or they may have a small NPU, neural processing unit. And today we've covered CUDA programming, but I mean, the general problem is really the same. In kind of like, I mean, it may be that your edge device doesn't have a tensor core, but still has kind of like a local shared memory that you have available. So unfortunately, every device is kind of slightly different. So it's really hard to kind of say, But usually, as with all things, you got to kind of know your device. Virtually all of them will have registers. Virtually all of them will have shared memory. Virtually all of them will have maybe a little bit of vectorization. The future, I think, is going to be NPUs, which are neural processing units within the CPU. So which will mean that there'll be a little bit like mini GPUs, mini tensor cores that are available for the AI bits to use. So I think this whole kind of like approach to thinking about the problem will be right, but because all the devices are different, although unless if you're on NVIDIA devices like the Jetson Thor or the Orin Nano, those are very much like GPUs, and you can actually program them using CUDA, the Jetson. It's actually a really nice device. For a couple of grand, you can get like the very latest kind of Blackwell type architecture. So yeah, because it depends on the device. For NVIDIA devices like Jetson Thor, you can use this as is because they're Blackwell architecture. But other devices from Qualcomm or from other manufacturers, they will almost always in the future have some sort of NPU. But right now, a lot of it, like if we're talking mobile phones, they do have like a GPU, but it doesn't really. It's more for graphics. So this is not suitable. But as I say, the overall mental model of okay, what is my memory hierarchy on the device? What compute units available? What kind of vectorization is available? A lot of those, the compiler might help you with a little bit, but as with all these things, you got to really know your hardware, basically. What's actually on it, and they're not all the same.
Cool. Thank you so much, Arshad. It's been really cool presentation, and I hope we all learn from it. Yeah, that's all for today's session, and we'll see you guys again in 2 weeks.
Okay, great. Thank you very much, guys.
Thanks, Arshad.
Thank you. Okay, bye.
Thank you.